So as Aaron said, I'll be talking about the new NASA mission called Solar Dynamics Observatory. Their logo is our eye on the sun. But we already have some observatories in space looking at the sun, so I think it should be called our new eye on the sun. A lot of the material you'll be seeing is from a big team of many scientists, both here at LASP as well as University of Southern California for one of the channels on Eve, Stanford University, Lockheed Martin, and also Goddard Space Flight Center. So there's hundreds of people that go into making a NASA mission. So a lot of the slides and movies you'll be seeing will be related to contributions from a lot of people. I'm going to take you back about 2 months. So back in early August, do you remember seeing news titles, headlines like this? NASA scientists brace for solar tsunami to hit Earth. Solar tsunami continues tonight, August the 4th, 2010, and beautiful colors light up the sky. Photos and video at 10 or whatever. You remember that?
Yeah.
So that's one of the examples why SDO is up there, is to understand these solar storms that creates things like Aurora, is what that light is talking about here. So first I'm going to give you an introduction about what is space weather. This is related to the weather in space. Space is basically above 50 miles, about 80 kilometers. Above that is where our satellite technologies live. And so we're concerned about the weather up there as well as, of course, our weather down on the ground for our own personal lives, but our technology lives up there in space. And the weather is associated with the current state of the atmosphere. And like any weather, we're concerned about what's happening today or what might be predicted to happen tomorrow. So a lot of that is related to the sun. And it affects technology like your GPS navigation system. It relies on satellites to transmit down where you think you are. So doing a big solar storm, your GPS navigation system could either become less accurate or even completely disrupted. Other communication satellites for your TV, radio, for example. There was a solar storm that knocked out one of the telecommunication satellites over Luxembourg, and they didn't have TV for a week, and they had riots and well, they didn't have TV. Airline flights, believe it or not, they have to reroute planes because of solar storms, especially the ones that go between continents, the ones that go over the poles. If there's a big solar storm, they have to reroute planes. That's millions of dollars a day they lose in fuel because of longer routes. And then, of course, communications, both on the ground as well as between satellites, but mostly satellites to ground communication. A lot of your gasoline services is based on communicating to a satellite to verify your credit card's good. So you could not be able to pump your gas if there's a big solar storm. And getting your gas or gasoline in itself is disrupted. So all the drilling in the Gulf, they have these mile-long drill bits to drill. If there's a big solar storm, because they rely on GPS navigation system to keep the drill bit very vertical, they don't want to be drifting around because they don't know where they are. So they quit drilling during a solar storm, or else they might break these $1 million bits. So, and especially since the Gulf oil leak lately, that becomes even more critical that we keep track of these solar storms. Another example of space weather effects that actually gets to the ground is when a solar storm goes off, it often releases a lot of particles, and we'll be showing you some movies of these effects. And those particles will get into our magnetic system here at Earth and charge up, kind of electrify our ground system. Ground wires charge them up and can blow out transformers, as an example here from a Canadian ground transformer for a power company. So these are just examples of space weather effects on our technology. So keeping our eye on the sun, when's the next storm going to go off, and predicting when the next storm might go off is what space weather is all about. One of the first space weather events is well documented and discussed even today. It happened in 1859. Richard Carrington was just sitting there looking through a solar telescope, looking at the sunspots, and all at once he saw a big white light flare. So this is his hand drawing of what this active region looked like. I don't know if you can see these little white things here. That's where the flare started. And it rippled all along this sunspot. Today we call these two-ribbon flares. It's probably one of the largest that we know of in the past 150 years. One of the effects is, of course, Aurora. We get those particles from not from the flare itself, but from the particles associated with the flare, gets to Earth and creates Aurora. It was so bright that people in Europe were reading the newspaper in the dark without any lights because of the Aurora. Another example of affecting our technology, even back then, is using telegraphs. So telegraphs were invented about 1840 by Samuel Morse, got it distributed all over the United States as a way to communicate with Morse code, the dots and dashes. So this telegraph system basically worked by burning little holes into the paper, and it used batteries and whatnot. So during this storm, they noticed they didn't even have to use their battery. There was so much current in the ground wires because of the solar storm that they just disconnected their battery. In some places, well, it caught the paper on fire. So even back then, even our limited technology was affected by these solar storms. So what's the sun doing today? Well, this is where we're going to talk about SDO. So this is an image from SDO this morning. Every 12 seconds, they're making many, many images of the sun. So this was I just happened to download it this morning, but you could go now and pick out what it's doing this moment. This is in white light. This is at 450 nanometers. This is looking at the photosphere. Do you see anything interesting? It's pretty quiet. You might be able to see a little active region right there. Well, we look at it in a different wavelength, different color. And we see a lot more activity. This is the same picture, the same sun, just a different wavelength. So if you look at the spectrum, basically if you take light through a prism or off a grating, you get the color spectrum. Here's an example spectrum of the sun. Here's an example spectrum of Aurora, which is a bunch of emission lines. But we're looking out here at the very short part of the spectrum that you can't see with your eye, the ultraviolet. We're looking at the extreme ultraviolet, even shorter wavelengths than kind of off this scale. And you can see the sun looks very, very different. I'll go back. Here's the visible light photosphere, and here's extreme ultraviolet showing you the hot corona. You can see already there's that active region that shows it's very large. It's not just a little tiny dot. You see corona holes, these dark regions. You see these prominences. A lot of this is the source of the solar wind. So you see a lot more in the extreme ultraviolet. So a preference for solar space weather is to look at the sun in the extreme ultraviolet. Now this radiation never reaches to the ground, and that's why we have to be in a satellite to be able to look at the extreme ultraviolet wavelengths. One of the things we do is look for flares. We're sitting here imaging the sun, and all at once a flare means brightening. It gets very bright. You can see the coronal loops here on the sun in the extreme ultraviolet getting very bright. And this is a very classic example of two ribbons where you see these coronal loops kind of in two ribbons. There's like a ribbon here and a ribbon there. And these are typically some of the largest flares. Almost always, not always, about 90% of the time when there's a flare, there's also what's called a coronal mass ejection. This is where part of the corona, these loops and stuff that you're seeing here, actually leave the sun. And if they're pointed at Earth, they can hit Earth and cause some of those effects that I was mentioning for space weather. So let's look at a coronal mass ejection. So this is just a picture. I'm going to show you next the movie, but I'm going to point out what to watch in the movie. The solar wind is these features that kind of just linearly coming out. The coronal mass ejection, you'll see kind of a circle kind of effect, and it'll be moving very fast. Whereas this is just kind of like a constant stream of particles. This is kind of an event that leaves much faster than the solar wind. Now the solar flare is photons. It gets here in 8 minutes at Earth. The coronal mass ejection, depending on its velocity, will get here in about 1 to 4 days. So we at least have a warning for coronal mass ejection. For flares, once you see it, you've already been hit with it. And there's other effects as well from flares, but the ones that I mostly was talking about, disruption for GPS and stuff, is usually associated with the CME more than just the flare. Although a big flare can disrupt the ionosphere as well. So here comes the movie. Does everyone clearly see that coronal mass ejection leaving? Now that one was taken at Earth, so that coronal mass ejection is going away from the sun. It's probably not going to hit Earth. The ones that's going to hit Earth, typically that circle, that loop there, would show up as a ring, and you see that ring expanding. That's called a halo CME. Those are the ones we get most concerned about hitting Earth. So one question is, why do we have all this activity on the sun? It's pretty much all driven by magnetic fields on the sun. Just like your bar magnet in the lab, you have magnetic fields going from the North Pole to the South Pole. On the sun, it's similar. You got, in a sense, a magnet somewhat below the surface of the sun, and you end up with almost always two sunspots. Two dark spots in the sun if you look at it invisible. One spot is going to be a north magnetic polarity, and the other one's going to be a south magnetic polarity. And over time, this will slowly pull apart and disperse, and it's hard to tell where the original sunspot may have been, but they always usually start as a pair. On Earth, we also have a magnetic field, as you well know. And the magnetic field here, we call this North Pole, but really it's the South Pole of the magnetic field if you have a formal definition. But nonetheless, it does have a magnetic field. And fortunately, we do have a magnetic field because it helps protect us from a lot of these particles. These particles are generally charged up particles, like ions or protons, electrons. So when and this is obviously not to scale, the sun is having a large coronal mass ejection. And notice how big it is. This isn't going across the entire almost surface of the sun here. As it gets to, and this is kind of elapsed in time, once it gets to Earth, this is our magnetic field. This magnetosheet here pushes most of the particles away so that they don't impact Earth. What happens is if they're really energetic, they just punch straight through. But most of them will just kind of wander off to the sides. When they get back out here, not shown here in the magnetotail, they mysteriously get sucked back into the Earth's magnetic field and just oscillate back and forth between the poles because the particles like to spiral along the magnetic fields. So most of those particles go past us because we have a magnetic field, but it does trap a significant amount of particles that it creates those space weather events at Earth. And one of the more beautiful aspects of a space weather storm is the aurora, primarily in the poles. Here's Aurora looking overhead in Alaska doing a storm, so it's a movie. This is Aurora with a reflection onto a lake. This is Aurora over Incar up on the mesa. This was in 2003. So yes, we can get Aurora as far south as Colorado. In fact, this storm was so big, it knocked out GPS as far south as Florida. No one had GPS for a couple hours. And people in Mexico, not New Mexico, but the country Mexico, could see Aurora. So every 10 years or so, you could expect to see Aurora even in Colorado. But it's not very frequent, although we did have one that reached as far south as Michigan just in that August 1st storm. So get ready. We're coming out of solar minimum now. We're heading towards solar maximum. We should start having more solar storms and more Aurora. So keep your eyes out for Aurora alerts if you want to go see them. You can also go farther north and see them more frequently. So this is kind of an introduction to space weather, effects of technology, and what we look for on the sun. Now we'll specifically talk more about the Solar Dynamics Observatory SDO mission itself. NASA has a program within the Heliophysics division called Living with a Star, star being our sun itself, kind of a cute title. And part of the objectives of living with a star is why does the sun vary, how does the Earth respond, and what's the effect on life and technology? That is, what's the space weather effects in general? SDO itself is the first mission for living with a star. It will be addressing that first question primarily, how and why does the sun vary? This is an example picture of SDO. It's a fairly large satellite. As you can see here, here's several engineers and scientists standing beside the satellite in the clean room. And this is down in the Astrotech clean room down in near Kennedy Space Center where we launched from. It's about 3,000 kilogram payload or satellite. It uses about 1,500 watts. What lasts in your house, typically. And we had a very, very perfect launch on February the 11th.
Solar Dynamics Observatory, learning why our star is changing.
I don't know if you can hear this, it doesn't matter if you can't. But. So this launched on Atlas V. I don't know if you saw the shock wave there. Now this is, of course, a cartoon of what happens. But this is releasing the SDO satellite, opening doors, and getting ready to take solar data. Now, of course, that happened over about a period of 2 months, but we got the speeded up version so that you can look at the data soon. So an interesting aspect of SDO is the large amount of data from SDO. When we first started defining the SDO mission was back when we were using SOHO, which has typically about 1K by 1K type images, 1 megapixel. This screen is about the same resolution. This is about 1K by 1K resolution. So SDO is 16 megapixels, 4K by 4K, 16 times more information than this. I'm going to be showing you SDO movies, but to show it on the screen, I'm going to be losing 16 times information. So you're not going to get the full quality of what's really being measured on SDO. But associated with this larger size is a larger volume. When we first started thinking about building this satellite, we needed 2 terabytes per day to take data off of this satellite. Today, it's not so scary. You can go to Best Buy and buy a 2 terabyte drive for $200 or something. Thank goodness technology kept up with us. When we first started, it was going to be like $1 million a day to buy 2 terabytes of data. So now it's $200 a day, no big deal. Here's an example early on in the mission. I'm going to let you watch it and see what you would call this feature. So watch this feature here as it erupts.
Is this real time?
Probably not. This is probably speeded up by factor 10. This one doesn't have a clock, so I couldn't tell you. Most of the times there's a little clock in the corner so you can see how fast. So who saw that Avatar movie lately? So this got named the Avatar Tree of Souls. I don't know if you noticed that. This was a little bit like that in the movie. I don't know. This came after the movie, but nonetheless, I guess we picked names. But this is a case of a prominence. It's eruption that actually doesn't leave the sun. It just goes up, and you see it come back to the sun. Those won't produce space weather events here at Earth, but they're pretty to watch. So the next few slides, I'm going to be talking about the 3 different instruments on board the SDO satellite. One of them is called HMI, the Helioseismic and Magnetic Imager. Dr. Phil Scher at Stanford University is the principal investigator. It's a fairly large instrument. I don't know, there's not necessarily a scale here, but it's about this big, this tall, about that high. So it's a fairly large instrument. It's not a huge instrument by any means. And it has a couple interesting measurements. One is measuring the magnetic field, but also it's measuring what we call helioseismology. It's kind of like seismology here at Earth, but helo meaning the sun, at the sun. And the interesting aspect of watching these oscillations on the sun is these modes of oscillations allow us to actually probe into the sun. So different frequencies allow us to probe different depths of the sun. So we actually image inside the sun with this technology. And this is an example of looking at how the solar structure is formed. Inside the core of the sun is basically a nuclear fusion reaction going off. It's fairly uniform with very hot temperatures at the core and, of course, cooler temperatures as you go out. But then we have the convection zone. And you got these basically oscillations of movement of mass going from the equator up to the poles, back down, and recirculating. So this is how our magnetic field is recirculated. This is called the solar dynamo effect. And because of helioseismology, they're able to measure this and understand some of this circulation. This solar dynamo effect is about, depending on whose solar dynamo theory you believe, and they're still debating over how fast this is moving from equator to the pole. There's measurements, but there's controversy in some of this. It's anywhere from 10 years to 50 years to go from equator back to equator. Now, you probably know there's 11-year solar cycle. So some solar dynamo models have one cycle is one solar cycle. Some have it, they get up here in one cycle, but they get kind of piled up down here, and then they pop up later. So a lot of the SDO will help answer how does the solar dynamo actually work. And we have the HMI instrument to help answer those questions. Here's an example movie. This is a picture first before the movie. You're just looking at the visible light, very high resolution. You're going to be watching all these little Dopplergrams, basically velocity of the features of the sun changing. So black is one direction, white's the opposite direction, either coming towards you or going away from you. And you're going to watch this movie of it just kind of oscillating. And that's part of what helioseismology is all about. This is a sunspot. You can see it's kind of one velocity instead of black and white, salt and pepper. So you see it oscillating. There's a natural oscillation of about 5 minutes, and that's where most of what you're seeing. You can see these features. I don't know if you can see it from way in the back, but these features on the edges of the sunspot are kind of expanding out with time. But it's hard to get real use information just watching this, just like watching a TV that died on here at midnight in the old days when they turned TV off. But that's the source of the data for HMI. In addition to the helioseismology measurements, that kind of salt and pepper kind of look, they also measure the magnetic fields. In addition to just measuring the magnetic fields, line of sight magnetic field, they also measure the vector magnetic fields. I'm not showing you any of that where they actually can tell you which direction each magnetic field loop is pointing. This one is the line of sight magnetic field, so you have basically two colors. One color, in this case yellow, is one polarity, black is another polarity. And as you can see, there's always associated together. So there's always usually both colors associated with any region. This is an old active region, so originally when this erupted, it was two really compact sunspots. It had one really intense black region, one intense yellow region, but this is decayed over, I would guess by looking at this, at least 1 or 2 months. The solar rotation is about 27 days, so this has gone around the sun a couple times. Here's some more active regions popping up. It's a little bit newer. You can see how they're a little bit closer, a little bit more compact together. And you can also see, I don't know if you can see the colors here as well as I can, but there's like predominantly kind of one color down here, yellow, and up here it's more predominantly black. And this is the feature of 11-year solar cycle. You reverse the magnetic polarity every 11 years, and therefore you actually have a 22-year magnetic cycle. The other thing you'll notice is each solar cycle they flip polarity. So this solar cycle the black is leading on the northern hemisphere, and the yellow is leading in the southern hemisphere. The next 11-year solar cycle will be reversed. Yellow will be leading in the north side, and black will be leading in the south side. But related to all these magnetic features, where all the solar activity, where all these flares and CME comes from. So they help, this instrument helps map the magnetic fields to the photosphere, but they don't necessarily show you where the storms are. So here's a movie first before I move on to the other instrument, showing you that same picture, but just watching it rotate for about a solar rotation. So you can see the different active regions coming on the sun. I don't know if you saw that, just immediately came up out of the surface of the sun. They're constantly erupting up out of the photosphere, and they take about 7 months for this to decay away where you can't really see it anymore. Sometimes they decay away faster. So the next instrument is called Atmospheric Imaging Assembly. This is a Lockheed Martin instrument. They've done a lot of solar instruments for a variety of satellite missions, both for NASA as well as the Japanese. And they have 4 telescopes for the ultraviolet. And primarily what they're trying to measure is the extreme ultraviolet images, like I showed you before. They give you a lot of information about flares, as well as coronal mass ejections as well. And they have many different wavelengths in the ultraviolet. Going in temperature, going counterclockwise, starting with sort of the chromosphere, which is the layer above the photosphere. This is a carbon-4 emission. You can see what we call the active network in the sun. There's active regions. We call that plage in the ultraviolet instead of active regions or sunspots. As you go hotter, we start going into the corona. So this is the chromosphere. This is the transition region. This is a bright helium-2 emission at 304 angstroms. And then the rest of these are corona emissions going from approximately 1 million degrees Kelvin, very hot temperatures, to about 10 million degrees Kelvin, so kind of in order of temperature. And you can see very similar features in all of these. The active regions, the coronal loops, the coronal holes, the dark regions. In some wavelengths, the coronal holes are more obvious than others. So these are the primary wavelengths we use for looking at coronas and looking for eruptions. One of the first flare or first prominences off of AIA, here's an example of Earth size compared to just a prominence. Huge effects, these prominences. And this is even a small one, relatively speaking, that can happen on the sun. So here's a movie of that. You can see it coming off. And interesting aspect, of course, it gets sucked back down into the system, but it's also twisted. You can watch it twisting back down. We call that helicity of these coronal loops. So fascinating. And to get you a perspective of how that is compared to the size of the sun, now watch this. It's a huge prominence. We see even prominences going completely across the sun. So this is large, but not the largest that we've seen on the sun. Another example that was somewhat a surprise for AIA, partially because they got better spatial resolution than previous measurements, is these waves that sweep across the sun. Now this has been known before. Some people have called them EIT waves or corona waves. So after a flare goes off, coronal mass ejection goes off, you'll see basically waves going from the northern hemisphere of the sun all the way to the southern hemisphere, and it's also getting dark because it's kind of getting rid of the corona temporarily, and then it kind of reforms afterwards. So this starts at different wavelengths. So in this wavelength, you barely could see the corona waves. See this one, you can see a little bit better. So different wavelengths give you different information. You're looking at different temperatures. See how that one went way down here? See how it gets dark and the wave comes completely down here. Were you able to see that? So these large global scale waves is a very interesting aspect. One question is it triggering other solar events? In other words, can one flare with these large waves trigger another flare somewhere else on the sun? Here's the same thing, but magnifying in on the region. So the same sort of thing, but trying to get you a little bit better idea of what the AIA image really is. So you can see a wave coming out, but it's not as obvious in the helium transition region emission. Now we get a little bit hotter. Go into lower temperature corona, about 1 million degrees. Start seeing more structure and just this whole coronal mass ejection. Go a little bit hotter. You start seeing a little bit more clearly these effects, these kind of waves propagating down, but also the coronal mass ejection kind of evacuating these areas of corona, getting very dark there. And the flare itself is in this region right here, but it starts this coronal waves and this coronal mass ejection that becomes more global scale. And as I mentioned before, this large-scale structure has been somewhat a surprise to the AIA team who's been studying these. This is a long-duration flare. It started and kind of just migrated for many, many hours along here. I'm not going to show you a movie, but basically this extent here basically covered half a hemisphere of the sun by the time it was over. So very large scale. And we tend to think of flares as very localized, but the consequence of the flare is very global scale of the sun. The third and final instrument is our instrument here at LASP called EVE, the Extreme Ultraviolet Variability Experiment. I'm the PI for this instrument, and there's about 80 to 100 engineers helped build this instrument, as well as the University of Southern California group, and the MIT Lincoln Lab helped build detectors. And this is a picture of the instrument. It's modest size. As you're leaving the lab, we have a prototype instrument of this instrument. We use it to calibrate once a year how this instrument's degrading. As you're leaving, there's a clean room area there that you can look in, and the prototype instrument is sitting in a shipping case. It's kind of got a static bag over it, so it may be a little hard to see, but it looks pretty much identically the same as that. It's about meter cube. And instead of imaging the sun, we want to take the spectrum. We want to take the colors of the rainbow in a sense, but in the extreme ultraviolet. And the reason why this is important is we get all the wavelengths. AIA only gets about 8 DUV wavelengths. We get all the wavelengths in the extreme ultraviolet. And Dean Pesnell, the STL project scientist, likes to call us the heartbeat of space weather because we get to watch all these wavelengths constantly going up and down. This is an example not from STO, but from our other instrument measuring the extreme ultraviolet irradiance called Solar EV Experiment on the Time satellite. This instrument will be turned off in this year, but you can see the 27-day solar rotation. If you look in the chromosphere, you can barely see those solar rotations. But as you get down into the corona, notice how these variations are very large. This is a log scale, so we're talking factors of 2 or 3 just in variations. We see a factor of 14 just in solar cycle variability for the shortest wavelengths. The solar variability that actually affects us on Earth, the climate, is only 0.1%, 1 part of 1,000. In these wavelengths, we're talking factors of 2 to factors of 100. So this is the part of the spectrum of the sun that varies a lot, and therefore it's easier to measure and easier to see these flare effects. So I'm going to show you an example of one of our flares. So what we watch for in a flare, we do have, I said we didn't make images, we do make one set of images in the X-ray. It's not 4K by 4K, it's only about 100 pixels by 100 pixels. It's an X-ray pinhole camera, so this is our X-ray image from Eve. It's not nearly, obviously, the same quality as you get from A or HMI. But nonetheless, it highlights the flares. When we have a flare go off, it's a very bright region goes off in the sun. What we often watch for in a flare is how it evolves over time. So this is time going here from, in this case, 18 hours and 20 minutes to 18 hours and 50 minutes. So this is 30 minutes long. And you'll see that different wavelengths are peaking at different times. We also watch the spectrum. So this is one small part of our spectrum, so you can actually see the individual lines. Each of these emission lines are associated with a different iron emission in the sun. Each iron emission has a different temperature. So in a sense, each of these lines are looking at different layers of the sun, or different parts of the corona. So as you watch this movie, you'll see each emission lines go up and come down and how they're different. And you'll see these lines going up and down. And what we're watching for from a space weather point of view is how these peaks are different in time, and how then we use these spectra to model on Earth real time. This is some modeling done at NOAA Space Weather Prediction Center just down the street here on Broadway. They plan to run about every 15 minutes to calculate the ionosphere and the thermosphere, that is the part where our satellites live, densities and temperatures, so they can better predict how our satellites will be impacted by these flares. So they're going to be using the Eve data to do those type modeling efforts. So one of the surprises from Eve is that we've been watching X-ray flares for about 50 years from a variety of different NRL satellites, as well as NOAA satellites, the GO satellites. And we have a pretty good feeling of what happens in the X-rays because we've been watching for so long. Typically they come up, they have a peak, and they kind of have an exponential decay. Until we launched Eve, or STO, we didn't know that there's actually extra peaks in the extreme ultraviolet we didn't know about, and these are very significant. So what you're going to notice as you watch this white line here is a typical hot coronal line that's very similar to the X-rays. It's going to go up, come back down, and go pretty much to zero. The red is a different iron emission. It's an iron 16 emission. That means it's lost. It's a 16th state of ionization, which actually means it lost 15 electrons. And you'll see it come down, but then you'll see it go back up. And this is a significant amount of energy. And you can watch the flare event here. Underlaid under this time series is an AA image of this iron 16 line. You'll see the flare go off here at first. This funny little checkered pattern is a diffraction pattern. They have like a mesh in their filter. So this is really not a solar feature. This is just a diffraction pattern from their mesh filter when they get extremely bright light coming through. So that's not real solar features, but you'll see the flare, which is solar features, get very bright. You'll see these coronal loops. If you look carefully, you'll see a coronal mass ejection. Right as the flare is starting, you'll see coronal mass ejection going off here. And then after this goes away, watch and see what you think causes this second peak. So the flare starts about here. So get ready for the coronal mass ejection. You'll see a kind of a wave going up very quickly. See that wave go up? And now it's come back down, and prior to STO, we would say the flare is over. But look what happens. These other UV lines are going back up. We didn't know this was happening on the sun. We didn't have the time resolution or spectral resolution with previous instruments to see this. So this is one of the big surprises for us on the Eve team. So we've been looking at and trying to figure out what is actually happening on the sun. What's causing this? So I'm going to show you a better movie, I think, that will show you this. This is still pictures getting you ready to watch the next movie. This is the beginning of the eruption. You see it getting very bright here. You see these coronal loops starting to rise. kind of the next in the sequence of things to watch for is you'll see the CME has already gone up, and these loops are starting to kind of collapse back on themselves. So this is kind of the end of the traditional flare period. And you also have what I would call the main flare phase in. So this flare, the brightening here has started to dim quite a bit. And then about an hour and a half later, not minutes later, an hour and a half later, you get this second peak in the iron Fit 16 emissions. And you'll see these loops here all at once start reforming. They've been heated up, and then now they're cooled down so you can see them again. And you'll see this, as they cool, they'll also start expanding out. So this is the source of our second peak. Is even though it's not associated with the original flare region below it, it was basically a recovery from the flare that caused it. So here's a movie, the same movie you saw, but multi-colors. The red and green are magnetic fields. The yellow is iron 9 emissions at about 1 million degrees. So there's the CME. You saw it go up. And then notice how dark it gets. This is because it's blown away a lot of this coronal mass ejection. It's also heated up so you can't see it at this temperature. And then as it cools back down, you'll start seeing these loops again. And that's the source of the second peak. So if we only had E and we didn't have AIA, we wouldn't be able to tell you what happened. And if we had AIA and we didn't have E, we wouldn't tell you that there was probably second peaks, because they're not looking at the variations like we are with E. So we see the spectral information and time resolution that they don't necessarily always see themselves. And as far as space weather applications, this is significant. A typical flare that we've been modeling is only about 21% of the total energy coming out of the extreme ultraviolet. About 80% of that energy is coming out of this second peak. It's not as tall as the first peak, but because it's so much wider, it has more energy. So this is sort of like discovering the icebergs. Before SEO, we were seeing the tip of the iceberg, and we see the whole thing. So I started with the August 1st headline news. I like to finish with the storm on August 1st. It was a long duration flare, one that lasted for a long period of time. It also had some major filament eruptions, or coronal mass ejections. There's actually 2 different filament eruptions. The flare is actually here. You see a CME associated with it. And I don't know if you can see this. This is the corona hole near the north pole of the sun. This CME is going to create this corona wave. This corona wave is going to come over here, and this dark band here is what we call a filament. It's kind of like a boundary between one polarity and one magnetic field and the other magnetic field. So it's kind of like a place of 0 magnetic fields. This whole filament is going to rise and go off. This whole band, almost 1 million kilometers long, is just going to go up all at once. Then that one triggers another one. This filament here then rises. This is over about 12 hours. So this one flare triggers all this activity for about 12 hours. So are you ready? Let's see if I can get it started. This is of course sped up, so you don't have to wait 12 hours to see this. But see that filament rising, and then this one comes up after it. Play it again. It is very quick, so there's the activity here that triggers this one up here, and this one then triggers that one. So huge coronal mass ejection. As far as a flare, it was a C-class flare. I don't know if that matters to you what that means, but it's a pretty small flare, but it had a very huge coronal mass ejection. In Eve, if you look at the Eve spectrum and its time series, the typical X-ray monitor on GOES would look like this. It had a very large flare and a very long duration. This is over many hours. Most flares are kind of like this, where he just goes up and comes back down. So this is what's called a long duration flare. In the iron 16 line, I was showing you where it has a second peak. This doesn't have a second peak like the other flare I showed you, but it does have a very delayed peak, delayed measurement. This is like an hour later than the X-ray. Another interesting aspect, this other iron emission shown here actually gets darker, it dims. And this is often associated with these cool corona emissions. You see that evacuation of the corona? So several emission lines will actually get dimmer while the coronal mass ejection is going off. So that was one of the first coronal mass ejections. You see some more effects here later. So we're learning a lot about the sun, how it, of course, is evolving, both for solar storms, flares, coronal mass ejections. And of course, an aspect of a storm like this is as far south as Michigan, they were seeing Aurora. It didn't get to Colorado, but it did get to Michigan. And perhaps the next storm will have a big one, and we'll see Aurora again in Colorado. So I'm going to end with this movie, and you can start asking questions. This is the 3 months of watching the sun with SDO. So thank you for your attention.